In this video, I'd like to take a look at hypothesis testing, or what I like to refer to as experiments to show change. In the world of continuous improvement and process improvement, hypothesis tests are one of the techniques that we can use. The specific learning objectives for this video include taking a look at hypothesis testing from an applied perspective. Then we'll take a look at the logic associated with setting up a hypothesis test or an experiment to show change. We'll look at interpreting the results using a statistic called the p-value. I've got two data sets right here with some descriptive statistics identified. And my question is there a difference between data set 1 and data set 2? Maybe this is current state versus future state. How could we show the rest of the world, the organization, or those in or outside of the organization that there is a difference between the two? Think about it for a second, come up with a list, and then let's come back and share our results. Okay, we're back now, and let's see if your list is similar to the list that I'd come up with. I think one way to show that there was a change would be to just compare the descriptive statistics, the central tendency, and the variation that was associated with it. We could set up tables. Another way to show if there was a change between the two data sets would be to take a look at the ability for the process to meet the needs of our customer, some form of process capability statistics, such as percent that are falling within spec. Another technique might be to take a look at the process capability metric CPK. Of course, we could do histograms and compare the histogram output. All of these are techniques that could be used to show that there was a change. But what if I told you that there was a black box, a box that if we started out with the two data sets side by side, and we could stick the data sets into this black box, the black box would shoot out an answer, and the answer would be that there was a change or there was no change. I put the frowny face next to the no change condition because in the world of process improvement, we're almost always hoping for some sort of a change. Change is important. It's important to show that we went from a frustrating current state to a better future state. I'd argue that using the tools that we've just outlined is probably the best way to show others and show your team that a change has occurred. But let's take a look at building a black box that could do it as well. That is really what a hypothesis test is. It's a black box that allows us to insert two data sets, and then it will send out an answer that there was a change or no change. All right, I've cleaned up my screen just a little bit, and let's dive into the concepts behind this thing I'm calling a black box. Our black box is really our hypothesis test. Hypothesis tests are just experiments to show change. So we've got a black box trying to help us understand change. I'm going to draw it right here. We're hoping that when we insert two data sets, the black box will tell us that there was a change. Change is good. Showing no change, well, that's bad. But we've got two data sets. I'm going to call one data set A, the other data set B. We're going to stick those data sets into the black box. Hopefully, the black box will show us that there was a change, and we can say, hooray. Sometimes the black box will show us that there was no change. No change is also the equivalent of saying if there's no change between A and B, that they're the same. Change means that they were different. So the logic's pretty simple. And that's the thing about black boxes. They're actually pretty darn simple. So unfortunately, here's what statisticians do. They take simple concepts, like the idea of a black box showing that there was change or no change, and they create more complexity by inserting terms and unusual logic. So let's take a look at some of the logic associated with this very simple concept of a black box. Okay, to help with the logic, I'm going to introduce a math problem. I'd like you to take a look at this math problem, -1 times -1, and you can pause the video, think about it, tell me what the answer is. All right, we're back. I hope that wasn't too difficult a question, but -1 times -1, what's the answer? You bet. It's +1. If you take a negative and you multiply by a negative, you're going to get a positive. We know that. We've learned that a long time ago in our early math classes. We've even practiced this concept at the grade school level, playing a simple recess game that you probably played, oh gosh, when you were 5, 6, 7 years old, out at the recess playground area. I'm going to draw a photo of this recess activity. Never have been much of an artist, but I think it'll be enough to explain this recess game. So I've got a photo of me and you as children at the recess playground, and the game was called the I'm Cool game. Here's how it would work. Uh, you'd be playing around at the playground. You'd run into some loudmouth. That'll be me. And I'd come up to you and say, I'm cool. And then the response that is typically given when you are 6, 7, 8-year old is, no, you're not. And then I'd come back and I'd say, but yes, I'm cool. And then you'd say, no, you're not. And then I'd say, I'm cool. And you'd say, no, you're not. And this would continue on and on again. I'm cool. No, you're not. I'm cool. No, you're not. I'm cool. No, you're not. And then what makes it a game is that at some point during this raging debate, I would introduce the statement, I'm not cool. And so it would look something like this. I'm cool, no you're not. I'm cool, no you're not. I'm cool, no you're not. And then I'd slip in, I'm not cool. And you would just, because you've been saying this so long, I'm cool, no you're not. I'm cool, no you're not. I'm cool, no you're not. I'm not cool. And then you would say, no you're not. And then I would go, when I said I'm not cool, and you responded with, no you're not. No, not cool. Saying no to not cool, a negative times a negative, is a positive. I'm not cool, and you saying no, you're not, equals I am cool. No, negative to a negative equals a positive. That's the exact logic that this black box is going to use. We are going to start out with a claim that the data is not different. I know we want the data to be different. We want to show that there is a change, but we're going to start out with a claim that they're not different. Let me write that down. I'm going to start out with the claim that A and B are the same. They're not different. Now, secretly, I want them to be different, but I'm going to start out with the no difference claim, the no change claim. I'm going to hope that the black box shows that there was a change by saying no to the no change condition. I'm actually going to hope that the black box shoots out no. Because by saying no to no change, really what you're saying is that there was a change, that there was a difference. See, this black box is using first, second grade logic. It's playing the I'm cool game with you. No to no change means that there is a change. Now, if you start out with the two data sets and say that there is no difference, that they're the same, and the black box agrees with you, well, if the black box agrees that there's no change, then there is no change, and they are the same. So no to no change is what we're hoping for when we use these black boxes. So I've just shifted the screen a little bit to give myself a little bit more real estate, and now let's go over the terms associated with this crazy logic of the no to no change black box condition. The first term that I'm going to throw out is that when we make our claim about the two different data sets, remember, let's zoom out just a little bit. Our claim is right up here when we're setting up the two data sets, and our claim is that there is no difference. Another way of saying claim is to call it a hypothesis. We're going to give it the acronym H for hypothesis. Now really, the claim or the hypothesis is the no change claim. We want them to be the same. A synonym for the word no. No sometimes means nothing. That sometimes can be the word zero. That in our British counterparts, they sometimes say the word zero is null. And so the no change claim, the no change condition, the fact that we're setting up the data sets and saying that there is no difference between them, we're going to call that the null hypothesis. And we'll label it as H sub 0. We'll call that the null hypothesis. It's the no change claim, which really means we're saying that they're the same. And what we want to have happen is we want the black box to say no to the null hypothesis. So if the black box says no to our claim of no change, that means that there was a change. Now, one way to say the word no is to use the phrase reject. So when the black box takes a look at our data and it shoots out a statement of accept or reject, reject means no. No to the no change condition means that there was a change. Rejecting the null hypothesis means there was a change. I know that seems a little goofy to be using grade school logic and surrounded by all of these jargon terms, but really a hypothesis test is a pretty simple tool. It's a black box that when you stick data in, you're hoping that it says no to the no change condition. You're hoping that it says reject the null hypothesis. If we see that the black box says reject the null hypothesis, we're excited because that means that there was a change. How do we know if the black box rejects the null hypothesis? Well, sometimes when you stick the data in, it'll just say reject the null hypothesis. That means there was a change. Other times what the black box will do is it will spit out something called a p-value. P-values help us to see if we can reject the null hypothesis. So let's take a quick look at what these p-values are. So I've got two data sets, A and B, and my question is how much overlap is there between the two? In this example, I hope that you came up with what I just wrote out. Yeah, there's very little overlap. There's probably none, or it's a tiny, tiny bit if we were to zoom in and see the overlapping regions between those two histograms. So zero overlap, what that means is that my p-value would be 0. P-values are going to range between the value of 0 and 1. If there's complete overlap, the p-value will be 1. If there's no overlap, the p-value will be 0. P-values will be some value between 0 and 1. And if we want the data sets to be different, if we want to reject the null hypothesis, we want very little overlap. So we want very small p-values. And we can have a high level of confidence that we are correct in our statement that the data sets are different. P-values are related to your confidence level to the point that if you want to be 95% confident, you want a p-value then that is 0.05 or less. Now, if I wanted 99% confidence level, it would be 0.01 or less for the p-value. So here's where we're at. We've got this black box. This black box is going to be used to help us to determine if there's a difference between two data sets. We set up the claim that the two data sets are the same. We call that the null hypothesis, the no change claim. We stick the two data sets into the black box. If the black box says no to no change, if it rejects the null hypothesis, it means that there was a change. Sometimes it won't say accept or reject. Sometimes it will use p-values. And if the p-value is less than 0.05, it also means that we can reject the null hypothesis, or in essence, we're saying that there is a change between the two data sets.